All right, welcome everybody. So here I'm going to try a new format where I'm going to try to do some quick videos where instead of going through the notes and doing them super thoroughly one by one, since I don't have the time to physically make those videos, I'm going to try to do some kind of quick bites where I'm going to grab a few of the examples from the notes and work those out, give full solutions to those, so I can kind of explain some of the tricks that I like to use. So for this first video, let's do sections 7, 1, 2, and 3. All right, so let's jump in. So here's our first problem. So chapter 7, it begins with a continuation of some trigonometric identities. Now, we have one here, but just to kind of summarize, there's a bunch of formulas. Let's see, let me pull up 7.1. So just to kind of briefly talk a bit about the difference between an equation versus an identity. So both of these are going to have an equal symbol in them, but conceptually there's a huge difference between the two. Now, how do I explain that quickly? Essentially, the difference is how many solutions are there. When we think about an equation usually has one or two solutions. Maybe there's three, maybe there's more. But think about something like x plus 1 equals 0. Now this is an equation. There's a variable x, there's some numbers and some symbols, but what makes this an equation is that it only has one solution, -1. Because if we plug in -1, we would get a true statement. -1 plus 1 is 0, but x equals to 2 is not a solution, right? If we plug in 2, we get that it's not true. So for equations, it's only going to be true for certain values of x. Now, what about an identity? An identity is something that is going to be true for every value. So think about the Pythagorean identity here. X squared plus y squared equals 1. Now this is true for all values, or let's say points, but not in general, only the points on the unit circle. So if all we care about is the unit circle, then as long as we're on that, x, the coordinates of the point on the unit circle, x comma y, let's draw a quick picture here, then those coordinates will satisfy this equation. So that makes it an identity. So another identity is the one right below, where we have cosine squared x plus sine squared x equals 1. It's also called the Pythagorean identity because that's, if you remember our derivation in class, it comes right from that and from the definition of what sine is and cosine is. Now, what makes this an identity? This is an identity because it's true for all x, all real numbers x. Not just for one value of x, not for two values, but for every single value of x that you plug in. Again, you're thinking of x here as a radian, so the wet noodle, so x can be as many turns around the circle as you want, but once you stop, cosine of x is the x coordinate, sine of x would be the y coordinate of the point, of the terminal point. All right, so that's quick and dirty definition of what an identity is. Now looking through what are the key identities, you just have to write these down. You have to make sure that they're correct. So since I type out the notes myself, please let me know if you see any typos so that I can fix it and let everybody else know. Again, you should have lots of formula sheets that I put in the handouts to compare. So if you see any discrepancy, let me know. I'm happy to fix them. So in chapter 6, we actually had a bunch of identities already. We had the Pythagorean and also the reciprocal identities. And then the even and odd identities. We didn't do too much with them, but the new ones are the cofunctions. I'm not going to explain them, but there they are. What I want to do is just kind of go over some of these tips next. So what are some of these tips for proving an identity? So I mentioned a little bit about this in class, but here it is in a nutshell. Okay, so the good advice is to start by looking at the complicated side of the equation. So if we look at the example 4 that we have right here, the complicated side is the left because the right side is 0. There's not much to work with. Also use the shorthand LHS or RHS for left-hand side versus right-hand side. That's just so that you don't have to copy the equation again. So for example, this is the left-hand side and the right-hand side is this. All right, so when you write a proof, what I'd like to see is that you put proof, and at the end of the proof, you put this little tiny square. The little square just signifies it's at the end of the proof. Okay, and then a proof just indicates that you're beginning. Now, remember, what is a proof? A proof is an argument to convince us that the statement or the claim that we are making is true. Okay? And then you can kind of read some of these common tricks here about things to keep in mind. It's a good handy thing to put on your cheat sheet. So if you're stuck on a proof on the test, you can be like, okay, let me look through these just to get some advice. All right, I think we're ready to actually start solving our first problem. So let's jump into that. Okay. So here we go. We are going to prove example 4. So let's start. So as I mentioned, we're going to start with the word proof. And we're going to start whichever side is more complicated. So let's start with the left-hand side. Okay. So you don't have to do this, but what I'd like to do it is I actually just like to copy the problem. Just so that I know with what I'm working. Now, as you look at this identity, you're thinking, okay, how do I get to 0? What's the first step that we can use? Now, the good tip here is anytime you see fractions, which is what we have here, you want to combine them into a single fraction. So that's going to be the trick that we're going to use. We're going to use, gosh, I'm using a new pen thing. Okay, that's too thick. Okay, that's good. We're going to use the common denominator trick, which means I need to have the same denominator in both fractions so that I can combine them. All right, so now through the beauty of digital writing, I can move things around. So what do I need to multiply my first fraction so that I can combine them? Well, I'm missing a 1 plus cosine theta. So I'm going to add 1 plus cosine theta to the top and bottom. Since again, this simplifies to 1. So what I'm doing is I'm basically multiplying my identity, my first piece of the identity by the number 1, which is not going to change my identity. That's why I can still claim that this is equal to the left-hand side. Because by multiplying this, I could always reverse it. I can just cancel those out and then I'm back to where I started. All right. Moving to the second term, I already have the 1 plus cosine. So the piece that I'm missing here is going to be sine theta. Again, same trick, right? That's just simplifies to 1. So I'm really not changing my problem. And that's why I can still claim that these are going to be equal to each other. All right, moving on. What's our next step? Next step is we're going to combine all of this into one super mega fraction. So we're going to multiply those two pieces on the top. Okay, then we're going to do minus, multiply those two pieces. Now they're the same thing, so we're going to write sine squared theta. And then what do we have in the denominator? We have sine theta times 1 plus cosine theta. All right, as we look at what we have done with just our common denominator trick, what's the next thing that we see? Well, pretty much, I'm going to look at this. This looks to be complicated, and I noticed something special about it. These are actually conjugates of each other. One of them is a plus, one of them is a minus, but it's the same numbers. It's the same as 1 and also the cosine. So the trick we're going to do is we're just going to straight up FOIL. What do we get? If we FOIL, we're going to get 1 times, so let's see, FOIL from the top, 1 times 1 gives us 1. And then for 1 times cosine theta is going to give us plus cosine theta. All right, let's FOIL from the bottom. We're going to get minus cosine theta times 1, so that's just a minus cosine theta. And then one more FOIL, minus cosine theta times cosine theta is minus cosine squared theta. All right, so those are our 4 terms from FOILing. Then we get minus sine squared theta that we still have to carry. All right, divided by, keep the last piece untouched. Okay, so from here, I hope you see that we've got some nice cancellation. We've got plus cosine theta, minus cosine theta, those disappear. We also have minus cosine squared theta minus sine squared theta. I hope you have alarm bells going off in your head and you're just dying to use the most important theorem in all of mathematics. But I'm going to make you hold your excitement for just a second. Let's factor out that minus sign and write it as cosine squared theta plus sine squared theta divided by sine theta times 1 plus cosine theta. Okay, now we can use our favorite theorem, and let's use bright green here. This, and I always like if you tell me when you use the Pythagorean theorem, so I'm going to highlight it in green and say Pythag, right, just Pythag for Pythagorean identity. Okay, and what does that equal? Let's put it in green. This is equal to 1. So, this is curious. We get 1 minus 1 divided by the downstairs. Now, what's 1 minus 1? That's 0. Is that what we were trying to get to? Well, looking back at what we were trying to prove, we were trying to get to 0. Now we got here. So before we finish, let's put equals, right-hand side, put the little square to indicate we have done it. It's the end of the proof. We started with writing proof at the top, and we have the little square, and this is an argument that shows you why those two sides are equal. We've shown everything, and if you think about it, really we only use 2 tricks. The common denominator trick to just get everything into one gigantic fraction, and then we also use the Pythagorean identity. Great. There's our first example.